Hi, this video will exploring the concept of isentropic efficiencies of a turbine. Well, we talked about isentropic before. Isentropic process, which means it's going to be, another word, it means it's internally reversible, right? Which means there's no friction at all. And also it's adiabatic, it's well insulated, there's no heat coming out of the system. So this is the most ideal situation. So I want to make a note that is ideal. So if you have a system like a turbine that's running in isentropic process, it's running its best. Right? We can always aim for that goal, but we cannot really achieve that because we cannot really get perfect non-friction situation. Okay, so knowing that concept, we're going to introduce this isentropic efficiency. So isentropic efficiency of the turbine, it's a ratio. So it's a ratio. We're gonna call this eta efficiency for the turbine. It's a ratio of this actual work output. I indicate actual over of the turbine to the work output. It's again output. Then that could be potentially achieved if the process is isentropic. So for the ideal situation, if this is S, which means it's isentropic. Okay, that's the best we could ever get, and this is actual. So the ratio between them, that gives us the isentropic efficiency of the turbine. So understand that now we're going to continue to explore. We know for the turbine, you have something comes in and expanded going out. And then in turn, we generate the shaft work, which is work out, right? And this work out is equal to enthalpy 1 minus H2. And we're going to times mass flow rate, and this is our work shaft output flow rate, right? So that's a work out power. And so knowing that, we can go back to this beginning equation here for isentropic efficiency. So the actual work out here will be equal to mass flow rate H1 minus H2. And the H2, it's a situation when it's actual situation, because H1 is the initial stage that stayed the same compared to reality versus isentropic, right? So this is the reality, the top one, the actual situation. And now let's looking at the ideal situation when this turbine runs beautifully without any friction. It's isentropic, it's reversible, there's no heat transfer. So in that case, we have mass flow rate. We're still going to use this equation. Starting initial enthalpy stay the same. However, the exit enthalpy will be a different scenario. Now it's going to be H2S. Okay, so knowing that, we can go ahead and cancel our mass flow rate. Then we get our equation for eta T, which is isentropic efficiency equation. That will be eta T is going to be equal to H1 minus H2 actual situation over H1 minus H2 for isentropic situation. Now here we go. We have the equation for isentropic efficiency of a turbine. Okay, so that's the end of the discussion for this one. I can't wait to show you an example of this. And this is actually a very important concept when people engineer working for power plant, and they need to know this value. Okay, all right, I'll see you then. Bye.